Hi, I'm Dan Hickstein, and I'm the principal scientist at Octave Photonics. Today, I'll be talking about how nanophotonic devices, like these colorful waveguides on the right of this slide, can be combined with electro-optic frequency combs to provide an excellent broadband source for astronomical spectrograph calibration. Before I get into the science, I wanted to provide a brief overview of our company, since most of you have probably never heard of it. Octave Photonics was founded in 2020, and we're located near Boulder, Colorado. You can see a photo of our lab on the left here. We're about 2 years old, and we're a spinoff from NIST and CU Boulder. We currently have 3 employees, and we're in the process of hiring a 4th. The goal of the company is to take nanophotonic chips and convert them into easy-to-use devices, like the one shown here. We're funded through a combination of commercial sales and federal funding from agencies like NASA, DARPA, and the Office of Naval Research. So in this talk, I'll give a brief background about how exoplanet detection works. Then I'll discuss how frequency combs can serve as an ideal calibration source for astronomical spectrographs. And finally, I'll describe how nanophotonic devices can facilitate calibration over a broad wavelength range. As you might know, finding planets orbiting distant stars is a challenging problem. We can't see these exoplanets directly. We can only see the light from the stars that they orbit around. So there are 2 primary methods for detecting exoplanets. The transit method is to simply wait for the planet to pass in front of the star, temporarily blocking the starlight. Of course, this only happens occasionally, and it only works for planets that happen to pass directly between Earth and the star. The radial velocimetry method relies on Doppler shifts in the starlight. As a planet orbits around a star, it pulls on the star, causing both the star and the planet to orbit around at the center of mass. This means that the star is periodically moving towards Earth, causing a blue shift in the light, and later in the orbit moving away from the Earth, causing a red shift. And the 2 methods are complementary, because the transit method provides information about the size of the planet, while the radial velocimetry method provides information about the mass of the planet. So if we can detect a method using both these methods, then we can estimate the density of the planet. At the observatory, the light from the star is recorded using a spectrograph. And if we periodically look at the spectrum from the star for many months or years, we start to see some shifts in the absorption lines as the planet orbits the star. However, we don't know if these shifts are real or if they just correspond to some slow drifts in the spectrometer. However, if we bring in some other light at known wavelengths, then we can correct for any drifts in the spectrometer and figure out which spectral shifts correspond to the Doppler shifts from the orbiting planets. There are several different options for calibration sources. First, there are atomic emission lamps. These are simple and relatively inexpensive, but the positions and intensities of the lines are unevenly spaced. And as the lamps age, the position of the lines can drift, which limits the precision of the measurement. Another option is to filter a white light source using a Fabry-Perot cavity consisting of 2 mirrors, like the one shown here. This produces evenly spaced lines with consistent intensities, so it looks like the nice ruler that you want. But it's difficult to stabilize the cavity to an absolute frequency calibration, so the position of the lines can drift from month to month. The ultimate option is to use a laser frequency comb, which provides evenly spaced lines with frequencies that can be absolutely calibrated to GPS time and remain accurate for years. The main downsides are that frequency combs can be expensive and complicated, but frequency combs are a rapidly evolving technology, and they're becoming more robust, reliable, and cost-effective every year. So what are laser frequency combs? Well, they're a special type of laser that emits regularly spaced pulses of light. In the frequency domain, this looks like a series of delta functions, which resemble a comb, so that's why it's called a laser frequency comb. The useful thing is that the frequency of each comb tooth is given by a simple equation based on the repetition rate of the pulses and this F0, or the offset frequency. So if we lock the repetition rate and the offset frequency of the comb to known radio frequencies, for example, from a commercially available GPS referenced oscillator, then we know the absolute frequency of every comb tooth in the comb. Laser frequency combs have traditionally been generated using mode-locked lasers. The first combs were free space titanium sapphire lasers, like this one on the left, operating at 800 nanometers. For most applications, these lasers have largely been replaced by erbium fiber combs operating near 1550 nanometers. These fiber-based frequency combs are easier to use and less expensive. However, commercial frequency combs based on mode-lock lasers typically operate with a repetition rate or comb tooth spacing of about 100 megahertz and aren't available with repetition rates more than about 2 gigahertz. These repetition rates are too low to be resolved by most astronomical spectrographs, meaning that it's difficult to use this type of comb for spectrograph calibration, although some tricks can be played to make this possible. But there's a different class of laser frequency combs called electro-optic combs. These combs are generated by taking a continuous laser and passing it through a series of electro-optic phase and intensity modulators. And the big advantage of this approach is that it allows us to generate combs directly at the 10 to 30 gigahertz repetition rates that are best suited for spectrograph calibration. While these EO combs have traditionally been used in research labs, Octave Photonics is developing a commercial version of the EO comb here, seen on the right, that's designed to bring EO combs outside of the lab. Working with these high repetition rate frequency combs presents some serious challenges, and one of these is supercontinuum generation. Frequency combs rely on the supercontinuum generation process to convert the relatively narrow bandwidth of the original comb to the broad bandwidth needed for spectrograph calibration. Also, broadening the comb to at least 1 octave is necessary to fully stabilize the frequency comb. Supercontinuum generation is typically done in nonlinear fiber, like the fiber you see in the image here. However, when using nonlinear fiber, the supercontinuum generation process requires about 1 nanojoule of pulse energy. At 10 gigahertz, this is about 10 watts, which is just not a practical amount of average power to get from an erbium fiber amplifier. Fortunately, nanophotonic waveguides come to the rescue. So what are nanophotonic chips? Well, just like we have microelectronic chips for electronic circuits, like this one shown on the left, we have nanophotonic chips for light. And just like these electronic integrated circuits can pack millions of transistors into a super tiny space, nanophotonic chips are starting to do the same thing for lasers and laser components. Additionally, these nanophotonic devices enable structures, materials, and functionality that's just not possible with traditional fiber or free space optics. Octave Photonics specializes in nonlinear nanophotonics, or nonlinear optics with nanophotonic waveguides. Nonlinear optics is a large field, but one of the primary goals is to take light at one frequency and convert it into light at another frequency, or a whole range of different frequencies. Traditionally, nonlinear optics is only possible when lasers have high peak power, but nanophotonic waveguides make it possible to perform nonlinear optical processes with much lower peak power lasers. These waveguides confine light to optical modes that are only a few hundred nanometers across, and this tight confinement of the light provides 2 huge advantages for nonlinear optics. The first is exceptionally high nonlinearity, and the second advantage is that this tight confinement allows us to change the refractive index as a function of wavelength, the dispersion profile. And so this allows wavelength conversion processes like supercontinuum generation to be phase matched. So on the right, you can see how a single chip can contain waveguides with different widths, which generate different color light, here spanning the whole visible spectrum when pumped with an infrared laser. So one really compelling application of these nonlinear nanophotonic waveguides is for supercontinuum generation. In the upper left, you can see a nanophotonic chip pumped with 1550 nanometer light, glowing with all sorts of colors across the visible spectrum, demonstrating the ability of these nonlinear waveguides to produce huge optical bandwidth and generate colors very far separated from the pump. The pulse energy required for this supercontinuum generation, as you can see in the figure on the right, is very low. In many cases, it requires less than 100 picojoules of pulse energy to produce a very broad spectrum, spanning much more than 1 octave of optical bandwidth. The ability to use these low pulse energies, this lets us do supercontinuum generation even with very high repetition rate lasers in the 10 to 30 gigahertz range. So nanophotonic waveguides have been successfully used to allow high repetition rate electro-optic combs to be used for astronomical spectrograph calibration. Notably, our collaborators at NIST have used a nanophotonic waveguide to broaden a 1 micron electro-optic comb, which was used to calibrate the HPF spectrograph at the Hobby-Eberly telescope in Texas. Using the nanophotonic waveguides, they generate huge optical bandwidth. They then use a spatial light modulator to generate the flat spectrum, as you can see in the purple graph there, that's required for the spectrograph calibration. This system has been used for finding exoplanets for several years, I think about 4 years now. And during that time, they've had something like 99% uptime. It's been really impressive. However, as you can see, this system is a fairly large, complicated system, and it takes a reasonable amount of remote and a bit of on-site maintenance from Connor, the laser expert on the left there. Fortunately, there's a number of aspects of this system that can be improved as we try to build the next generation version. So one of the things we can change is that the electro-optic comb setup at the Hobby-Eberly telescope used bare nanophotonic chips. And so on the left, I'm showing a typical laboratory setup for coupling light into and out of a nanophotonic chip. It involves fairly expensive precision alignment stages, a microscope, an enclosure to protect this delicate component from dust or other contamination. And it's a big, expensive system. What Octave Photonics is trying to do is to replace this huge setup with a fully packaged device. So this device, seen on the right, is one example. Features fiber connectors for simple connection of the nanophotonic chip to the laser. And it encloses the chip in a rugged package that allows it to operate outside the laboratory. And the packaged device, it also provides a huge reduction in scale, going from the full laboratory setup that extends over about, the better part of a meter, and it's replaced with a packaged device that's only a few centimeters long. So over the past few years, Octave Photonics has developed techniques to package nanophotonic chips into ruggedized fiber-coupled devices. Our packaging methods have low loss coupling from fiber to chip and can withstand very high average and peak intensities. So this allows nanophotonic chips to be used much more easily and in a much smaller area and at lower cost. We are currently working on a grant from NASA to develop a next-generation system for calibrating astronomical spectrographs, which combines an electro-optic comb and a specialized nanophotonic device. This system makes a number of improvements over the system used at the Hobby-Eberly telescope. First, we replaced the complicated nanopositioning stages with a simple packaged nanophotonic device. Next, we can get rid of the secondary low repetition rate frequency comb by broadening the electro-optic comb spectra to a full octave, which allows for direct F2F stabilization. We can also remove the free space gratings using on-chip pulse compression. And finally, we eliminate the bulky spectral flattener by directly generating a flat spectrum on the chip. So how do we generate the flat supercontinuum? Well, one trick we use is to change the width of the waveguide at a critical point during the supercontinuum generation process. This makes a sudden change in the dispersion profile of the waveguide and allows us to generate reasonably flat supercontinuum. Then, using a special nanostructure generated through an inverse design process, we can split the light into two paths, where the 780 nanometer light is sent into one waveguide for F2F self-referencing, and the rest of the supercontinuum light is sent into another waveguide for spectrograph calibration. This structure can also be designed to provide the appropriate wavelength-dependent attenuation to flatten the spectrum. So putting all this together leaves us with a really nice system for calibrating astronomical spectrographs across the 800 to 1300 nanometer region. But what about the other spectral regions? Well, since we're starting with a 1550 nanometer laser, generating light across the near infrared is relatively straightforward. And we've built several package waveguide devices that cover the 1800 to 2400 spectral region with reasonably flat spectra. The spectrum of one of those is shown on the upper left here. These devices have been proven to operate with a 16 gigahertz EO comb with about 3 watts of average power. And they will be installed at the Keck Observatory sometime, probably early next year. The visible wavelengths are somewhat more difficult. We've successfully generated light, as shown in the upper right here, down to about 550 nanometers. But going to the blue part of the spectrum is more challenging, and that will likely require more sophisticated wavelength conversion techniques, which we're currently investigating. So what does the future of frequency combs look like? Well, one path towards making frequency combs much smaller and with less power consumption is to use microcombs, which are based on microring resonators. Using microcombs, we can generate a frequency comb right on the nanophotonic chip, potentially using much less power than a traditional laser frequency comb and putting it into a much smaller package. Microcombs have already been demonstrated for precision radio velocimetry. However, the spectra, as you can see in the upper left, the spectra have been reasonably narrow. Under a new grant from NASA, Octave Photonics has recently started work on developing a broadband microcomb device that could be used for calibration of astronomical spectrographs. In the long run, such a device could be made very compact and with low power consumption, such that it would be compatible with the calibration of space-based spectrographs. So let me conclude with a summary of the main points of this talk. First, frequency combs provide an ideal calibration source for precision radio velocimetry. Second, electro-optic combs offer the 10 to 30 gigahertz repetition rates that are well suited for the resolution of spectrographs. Finally, nanophotonic chips can be used to convert EO combs into broadband sources that are great for calibration of these spectrographs. So for more information on what Octave Photonics is up to, you can check out our webpage. And for news and other updates, you can follow us on LinkedIn. And with that, I'd like to thank you for watching my talk. And if you have any questions, you're welcome to contact me via email at this address here. Have a great day.